Hi everybody, this is Mr. Short. Today you can see we're going to be working on 3.1 Introduction to Lewis Structures, and to introduce this concept we're going to learn how to draw Lewis structures for each of these three substances right here. Before we get to that though, some important background information. We've got to understand how to count valence electrons, so I want to review that real quickly. Remember, for elements in the 8 main groups, what we do is we take a look at the main group number, which is 1, 2, skip a few, 3, 4, 5, 6, 7, 8. That main group number tells you the number of valence electrons. So for example, hydrogen would have 1 valence electron, and oxygen, for example, would have 6 valence electrons. I want to point out before we get started that we're only learning about Lewis structures for covalent molecules and charged polyatomic ions. So just to review that concept, remember we've got the metalloid stair-step line right here. Covalent molecules combine multiple nonmetals. The nonmetals are to the right of that metalloid stair-step line, and hydrogen is the only nonmetal that's on the left side of the periodic table. All right, so again, the main idea right here is that the element's main group number tells you the number of valence electrons in that substance. Also, you can see from the structure of this paper that we've got 5 steps. We need to follow those steps in order for drawing Lewis structures for covalent molecules and for charged polyatomic ions. It always starts with step number 1, which is to add up the total number of valence electrons that should be included in the final Lewis structure. I just like to make a simple accounting table for this. So in the first substance that we're working with, we've got nitrogen and 3 hydrogens. You can see that nitrogen has 5 valence electrons, and each hydrogen has 1 valence electron. So in the accounting table, it will look like this. So we've got 5 plus hydrogen is 1. But we've got 3 hydrogens, so that's going to equal a magic number of 8. The total number of valence electrons always has to be even for Lewis structures. The reason is because electrons always come in pairs. So because they come in pairs, you always have to have an even number of valence electrons. The next thing that we do is to draw a skeleton structure. For the skeleton structure, we need to figure out which atom is in the center, and then we need to surround it with each of the peripheral atoms connected with single bonds. For the central atom, I want us to write this note out to the side. The central atom is always first in the formula. Okay, so for that reason, nitrogen is going to be in the center, and it's going to be surrounded by each of the 3 hydrogens. I want to put a subnote right here, so I'm going to put it in parentheses. Hydrogen is never the central atom. So H is never in the center. So for example, even though in water it's H2O, the hydrogens would not be in the center. It would be the oxygen that's in the center. So here's our skeleton structure with nitrogen in the middle, surrounded by the 3 hydrogens. You might remember in the pre-post learning concept check that I told you that we need to basically space out the peripheral atoms as far apart from one another as possible. Well, I know coming up here that there's going to be something placed right up here. That's why I've spaced them out like this, and you guys will learn how to do that also. All right, one reminder here. Remember that every bond, every stick, counts as 2 interacting valence electrons. So we've got 2 valence electrons here for 6 total valence electrons. Okay, so you need to train yourself to count by 2 when you're working with Lewis structures. So we've got 2, 4, 6 out of a total of 8 that we need to have. Keep that in mind. Step number 3 says add 6 more electron dots to each atom except for the central atom, also never to hydrogen. The hydrogens are always only going to look like this. They only have the capacity to hold 2 electrons, so each of these hydrogens will always look like this. They've got what you might refer to as a stable duet of 2 electrons. So again, this says add 6 more dots to everything, but not the central atom and not hydrogen. Well, if we can't add them to the central atom and we can't add them to hydrogen, then we need to skip step 3. Step number 4 is about leftover electrons. We've used 6 electrons, but we need to use 8 electrons, so we've got 2 leftovers. Leftovers get placed on the central atom. Okay, so if you take a look here, we've now used 2, 4, 6, 8, and we want to use 8. Also, we need to ask ourselves, step number 5, is the central atom following the octet rule right now? Well, the central atom, nitrogen, is following the octet rule, so for that reason we're done. You can see that it's got 2, 4, 6, 8. That's our final structure right there. Here's another example. Carbon dioxide, CO2. So each carbon, there's only one actually, carbon is going to have 4 valence electrons. Each oxygen is going to have 6 valence electrons. So I make a simple counting table. It looks like this. You've got to remember that we have 2 oxygens in carbon dioxide. For this reason, it's 4 plus 12, which is 16 total electrons in our final structure. That's step number 1. Step number 2, skeleton structure. Carbon comes first, so it's in the center. Connect it with single bonds and space out these peripheral atoms as much as possible. These atoms off to the side. You can see that I've used 2, 4 out of 16 electrons right here. Step number 3 says to add 6 more electron dots to each atom except to the central atom, also never to hydrogen. Okay, so we're not going to put any right now on the carbon. Now listen to my counting. I've already used 4 electrons, so I'm going to start my counting at 6, and I'm going to stop my counting at 16. So here's 2, 4, 6, 8, 10, 12, 14, 16. I've used all 16 electrons, and I have 16 to use. So I don't have any leftovers for this step right down here. Take a look and do some quick accounting with me. You should be able to spot that this oxygen has 8 valence electrons around it, because each dashed line represents 2 interacting valence electrons. So I've got 2, 4, 6, 8. That oxygen is identical to this oxygen, so this oxygen also has 8, but that central carbon only has 4. So take a look. Step 4, there are no leftovers, so we skip down to step 5. Step 5 is about the central atom in the octet rule. Step 5 says if the central atom has 8, then you're done, but if it doesn't have 8, then we need to cross out and share. Remember, that's what I taught you covalent bonding is about. Covalent bonding is about sharing, so I'm going to cross out and share. By doing that, you can see that this oxygen had 8 before, and it still has 8 now. It's got 2, 4, 6, 8. I'll draw that a little bit thicker right there. This oxygen, it still has 8. 2, 4, 6, 8. The carbon, it used to have 4, but by sharing, now it's got 2, 4, 6. You keep crossing out and sharing until your central atom has a stable octet of 8 valence electrons. This carbon now has 2, 4, 6, 8. Each of the peripheral oxygens also has 8. For that reason, we're done. One thing to point out is that by crossing out and sharing, we haven't changed the total number of electrons. We had 16 total electrons before crossing out and sharing, and we've still got 16 right now. So if you listen to the counting, you're going to see that we still have 16. 2, 4, 6, 8, 10, 12, 14, 16. Everything is following the octet rule. Okay, last example here. Hydroxide. Remember, hydroxide is a charged polyatomic ion. We have a list of 9 common polyatomic ions on the back of our periodic table. Hydroxide is one of them. It's right here, OH with a -1 charge. Oxygen has 6 valence electrons. Hydrogen has 1 valence electron. So when I do my accounting, it's going to be 6 plus 1. And if we stop there, you would notice that we have an odd number of valence electrons. We have to think about this charge right up here, and you need to ask yourself the question, does having a negative charge mean that something has gained valence electrons or lost valence electrons? Because electrons are negatively charged, to have a negative charge means that there must have been a gain of valence electrons. Because we gained a valence electron, we need to add +1. So again, you've got to train yourself to think opposite about those charges. That's going to give us an even number of valence electrons, and it's 8. when we draw the skeleton structure, this is a little bit different because we've only got 2 atoms, so we don't really have a central atom. So I'm going to go OH. It's going to be our skeleton structure right there. Step number 3 says to add 6 more electron dots to each atom, but not the central atom, and never to hydrogen. So according to step number 3, we can't really do anything with this right now. So we can skip down to step number 4. It's about leftover electrons. We've used 2 out of 8, so we've got 6 leftovers, and we're never going to put any electrons on hydrogen. So listen to the counting. Here's 2, 4, 6, 8. So again, it says leftover electrons are going to be placed on, it says the central atom, but we don't have a central atom, so oxygen is the best that we can do for that. Now we skip down to step 5. Step 5 is both about making sure that everything is following the octet rule, with the exception of hydrogen. And if you look down here at the bottom, it says if you have a charged polyatomic ion, then you place brackets around the final structure, and you put the charge in the upper right-hand corner of the brackets. So because this is a charged polyatomic ion, I'm going to put it in brackets, and I'm going to put the charge right up here. Basically, it kind of means this. I sort of think of these brackets as if they're a piece of toast, and the charge is butter. It's kind of like the butter gets spread across the background of these atoms. And it's sort of like we can't point to one particular place and say that's where the charge is at. That's kind of what the brackets and the charge mean. Just remember that anytime you're working with a charged polyatomic ion, the bottom of step 5 says you put it in brackets and you put the charge in the upper right-hand corner. Okay, that's an introduction to drawing Lewis structures. Thanks a lot, guys. See you soon.